Okay, so now we've studied all the details of reflection, all the details of refraction at plane and curved surfaces. So that means that we have all the tools we need to understand the lens. And I've made reference to this at the end of the last section there. And you no doubt know what this is because it's a regular word in English, but a lens is an optical system with two surfaces which refract light. So the curvature of the lens is what determines the focal point, which is something that we've identified. And thus lenses can be designed with certain geometry necessary to form an image at a desired location, like your retina in the case of your eyeglasses, right? So you want the clear, crisp image to arrive exactly at the point where you are receiving the information at your retina. So we're going to stick with the case of spherical surfaces when talking about lenses. And one additional simplification that we'll make is that we'll only be talking about thin lenses. And this may seem like another gross oversimplification, but it turns out almost all lenses that you've interacted with are thin lenses. So thin lenses are lenses that have very little separation between its two surfaces, such that the distance between them could be ignored. So your eyeglasses, for instance, are thin lenses, even though you can definitely see some macroscopic thickness there. All that it really means is that the object distance and the image distance, one or the others, or both, is so large compared to the thickness of the lens, the separation between the two surfaces on the left and the right of the lens, that we can come very, very close to the real solution by just ignoring the separation between them. That's all that means. So here is our familiar ray diagram for a thin lens. I'm going to draw it. So we have a surface on the left, and we have a surface on the right, like this, right? And we have an optical axis going right through the center of it, somewhere right about there, maybe a little higher. And we are going to identify the very center vertically between the two surfaces, like this, and we're going to call this, point O. We're going to declare this to be the focal length of the left side, and this to be, the focal length of the right side, there. And they're the same. I may not have drawn them the same, but they're the same. So we're going to consider an extended object right here, something like that, with height y. This is going to be our point P, and this is going to be our point Q up here. And that makes from here to, I'll do it lower. That makes from, got a big diagram this time, from here to there, the object distance s. And you say, well, wait a minute. The surface is like out here. Why did you go all the way to there? Well, because for thin lenses, remember what we are assuming is that there's virtually no separation. So in terms of how big the object and image distance is, whatever this is, you can think of it as that that delta amount again, right? That it's just so small that it really doesn't matter. And so typically, conventionally, we go right to the center of the lens for object distance and image distance. All right, so that means that we have an image over here. Oops, not at the focal point. Every time I try to open up the windows, get some fresh air, the world goes crazy. And this is going to be our point prime, P prime here, height y prime, and out here, Q prime. All right. So again, this is going to be our focal length. I kind of mentioned this, but I'll just write it here. I'll do this. So from there to there is focal length, and also from there to there is focal length. All right, and then we have our image distance. To right about there. All right. Alrighty, so now we're just about ready to start drawing some of our rays. I did do it quite big, so I'm going to zoom out just a tiny bit here. So, from the top of the arrow, we're going to go straight into the lens here, like that. That's about as straight as I can see. And we're going to say that that hits at point A. And then that is going to, that's going to refract down to, I am asserting anyway, and I'm sure by now you believe me, down to our point, the tip of the arrow of our image. And then we're going to do another ray, which is going to go like this, straight through. I'm going to have to adjust my image. I forgot to do that after I do my rays, like I usually have learned to do. So here we go. Something like that. I'll just redo. Alright. So this is our point Q prime, P prime, Y prime, and we have that one ray to follow back up with. So that means that this, alright, bear with me, needs to be where this crosses, because that's what happens there. So F2. And then this one's likely to be not exactly where it needs to be, because the other ray is going to go from the tip through the focal length on the left side to the end of the lens, like this, which puts our focal length right about here, F1. Hopefully those are close to the same size, same distance away from the center there. And then this, yeah, all right. So if you want a better drawing, reference the lecture notes. I think it's going to take a few more minutes to get this perfect, but know that this is supposed to be right there, and it's just the way that I've drawn the lens imperfectly, and probably this needed to go up a little bit, but I'm not going to waste your time by redoing it. Just reference the lecture notes there for that one, because that bottom ray doesn't really matter too much for what we're going to be doing. All right, so now let's figure out some angles here. So this is going to be alpha. This is going to be alpha also, of course. This is going to be beta, and also thereby this is beta. And we're ready. Okay, so now we have our image. Let's talk about what's going on here. So we have an extended image, extended object on the left, and a resulting image on the right. The ray QA Q prime, that would be QA Q prime, right? That top ray shows one bend right at the center of the lens, center vertical. This is to emphasize that this is a thin lens, like I had said before, where the distance and therefore refraction between the left surface and the right surface is to be ignored. So this same ray, QA Q prime, approaches the lens parallel to the optical axis and then is refracted such that it intersects with all other rays at the focal point. Similar to the refraction at a spherical surface we just studied. Ray QO Q prime crosses the thin lens undeflected because the two surfaces of the lens are parallel at the center, and because as a thin lens we are ignoring the distance between them. right? So the way that I've drawn it, it doesn't look like this is what's happened at all, but if this crosses exactly at this center point here, you got to imagine, in essence, what you're doing is you have two parallel surfaces and a ray is coming through like this. So yeah, it's going to like be deflected a tiny bit, right? But if you're considering them to be right next to each other, that deflection is ignored as well. So that just goes straight through. So we're seeing this blown up, exaggerated picture of it, but no, the reason why it goes straight through is because here and here it's parallel, and we're considering it to be essentially right next to each other. So there's no refraction or deflection there. All right, so when the object is placed outside the focal length f of the lens, like we've drawn, the final image that's formed of this extended object is real, and it's inverted. So that's what we see there. If instead we place the object inside the focal length, I'll tell you the image is virtual, it's erect, and it's larger than the object. And it's on the same side of the lens as the object. So you can go see that picture for yourself if you'd like. But I'll just tell you that. And if all this seems like actually a lot to memorize, because we talked about reflection at a spherical surface, refraction at a spherical surface, we got convex, concave, we got all kinds of sign rules, we got thin lenses now with new rules. If it just seems like a lot, don't worry, because in physics we seek to understand instead of memorize, and so it's not really I'm presenting you all these cases that you have to just tack on to a catalog of memorization. I'm just using these as the most common cases or the easiest cases to arrive at our equations, and the equations are really what allow us to solve the whole class of problems. So once we get to our equations, then we can algebraically solve from there and don't have to memorize all of the properties. We just need to know our sign rules and this and that if we want to evaluate for different cases. All right, so here's a game plan for the rest of this lecture. We're going to derive what's called the thin lens equation, which is identical format to these types of equations. It just gives an object, an image, and a radius of curvature or focal length relation for thin lenses. Then we're going to derive the lens maker's equation. So if you are a lens maker, you need to know how to make the lens according to certain specifications, and it requires a really interesting derivation to arrive at. But in the end, it gives you a relation between not only the object distance and the image distance, but it also relates the indices of refraction and the radius of curvature. So, or it goes through the object distance, image distance, but in the end, all you're left with is the index of refraction of the material that you're using to make the lens, the radius of curvature of the left side of the lens, radius of curvature of the right side of the lens, and the desired focal length. So it's really useful if you want to actually design one of these lenses. So when we're looking at the optics of it with thin lenses, we usually just say, we're ignoring the distance between, and we're treating the thin lens as like one refractive event. But for the thin lens, the lens maker equation, you have to treat it as two different refraction events because you have two different interfaces, so we have to get into that. So that's a really interesting derivation. And then the third thing is we've been going over all of the derivation and theory, but we've really not talked about any application or any problem. So I want to do one problem that is kind of a representation that kicks off the rest of the applications. So most of these optical applications involve a series of events that happen. So you have a few lenses put together and all the lenses are different, or lenses and mirrors that are put together. And it forms an image that you want, either magnified, and it's like, whatever the system is, a camera, a human eye, telescope, binoculars, opera glasses, whatever application you want to look at, all of them just come down to you have multiple of these same events going on, so you just string them together. So what we're going to do is we're going to look at an example of an image of an image. So just you have an object on the left, you have a lens, and then you have another lens, and what is the resulting image at the end of both of those lenses? And I think that's representative of all the rest, because that's really all that it comes down to. It's just multiple things in a row. So that's the game plan for this section. So next, we are going to derive the thin lens equation.